go through so that when you do it, you'll be doing it correctly. Okay, the first thing we're going to do is find the volume of all materials. And once again, the textbook decided to lump all of the uranium together. They should not have done that because there is going to be a slight difference in values depending upon what you have for your other isotopes of uranium, what the enrichment is. So we can find the volume of the graphite. I'll just put carbon. It's going to be the number of moles times A divided by the density. So in this particular case, there were 200 moles. A is 12 for carbon. If you go in the back of the book, the density, and they've already given you this at the top of the page, is 1.6. So they come up with a value of that of being 1,500. Instead of lumping all the uranium together, we should do the volume of U-233 as well as 238. If we do 233, if you go back, we said that it was 5% enriched for 1 mole. So this is 0.05 for U-233. This is 233. And the density, which they've listed at the top of the page, is 18.9. Multiply that out, you're going to have a value for that. We then need to look at the volume for U-238. We know that's the balance of the 1 mole, so 0.95 times 238. And again, the densities among all the uraniums, for each isotope, it's only 1 neutron difference, so it's essentially the same. And that will give you a value. We're going to add this value to this value to this value. I don't know if anybody's done that yet. We can just generally use the value that they have there. It's going to be very close to that. So let's make this value, well, somebody has a calculator, let's do that real quick, just so we'll have some good numbers going forward. So I got 1512.57 for the total volume. And I specifically accounted for each moderator and each of the 2 fuels that are there. And the next thing we're going to do is divide that into Avogadro's number. And that should have been 6.023, not 024. You're going to have a slightly different number than this. Let's say it's going to be this. If we then take this number and multiply it by the number of moles, we now have the number density of each material. We now need to go back and find values for microscopic cross-section for transport and microscopic cross-section for absorption that we can then put into a formula to find L, which is our thermal diffusion length, and then use that with our earlier value for K infinity to find buckling. So let's do sigma transport for thermal is equal to N sigma scatter for thermal times 1 minus the average value of scattering for each material. So we're going to go from 1 to N for however many number of these that we have. In this particular case, we have 2 fuels and 1 moderator. So if we do the moderators first, so we're going to have N carbon, sigma S thermal for carbon. This 1 minus the average value of the cosine is one minus 2 over 3A for carbon. And then we're going to add to that N 235, sigma S 235, again thermal, 1 minus 2 over 3A for 235. And then we're going to add to that N 238, sigma S 238 thermal, 1 minus 2 over 3A for 238. So where do we get this number? That's the number you just calculated right here. So you can put this number in here, this number in here, this number in here. You're going to get your microscopic cross-section for each of the materials. Remember, it's thermal from the back of the textbook in table A, and that value comes out to be 4.8 barns. This next one comes out to be 233. Excuse me, for 235, it's going to be 10. barns. This value is going to be 3 times 12. This number is going to be 3 times 235. Again, this number came from down here. Scattering for 238 in the back of the textbook is 8.3 barns. And this has become 3 times 238. You're going to do all that algebra, and you're going to come up with a macroscopic cross-section for transport, which is a version of scattering for our thermal neutrons. And just to save time here, we're going to say that it's slightly different than the value in the book, and I'm just going to invent a number, 0.37. It's going to be whatever you do when you calculate all of that. It's going to be close to the number in the book, but we've broken it down to show all the components. Any questions on how we did that? Okay. The next thing we're going to do is we need to find the absorption cross-section for our mixture. And to do that, we need this for each of our materials. So this is going to be the sum of all of these cavity materials we have. In this case, we have 3. So it's going to be N for carbon, sigma A for carbon. And again, this is thermal because we're considering all of our neutrons to be thermal. Plus N 235, sigma A 235, plus N 238, sigma A 238. And again, all of these are thermal values. When you go to calculate that, this value is this value we found. This value is this value that we found earlier. This value is this value that we found earlier. Then you're going to go in the back of the textbook and put in the values for absorption thermal for each of those. So for carbon, let's go to the back of the book and look. So for carbon, my absorption cross-section is 0.0034 times 10 to the minus 24th to get the proper units. For 235, when we go and look at that, remember that is the sigma A is the sum of sigma for fission plus the sigma for the parasitic loss. So that was 582 and 112. So this is 694. And then final for 238, that value was 2.71, which is 10 to the minus 24. Notice in the solution that you have, they're multiplying this number times square root of pi over 2 times 293 over t. So they're multiplying all of this times this. That's wrong. Why is that wrong? It's because this is a correction to correct for something that's epithermal that's not thermal. We know that everything we're talking about is thermal. So that does not come into play. Do not use this as a multiplier. This is strictly your macroscopic cross-section for absorption, the way it should be done. And you're going to come up with a value for that, and that's going to be different than what's in the book. So let's say that that value comes out to be, and again, I'm just going to invent that because we don't have it right now, 0.02. Once we've done all that, we can calculate L.
Professor.
Yes.
Okay, just to be clear, the corrections for the example in the book would be calculating the volume for 235 and 238, and then eliminating that square root of pi over 2 part.
In other words, whenever you're calculating the total volume, you must consider all materials. So that's moderators and fuels. In our particular case, for the example problem in the book, we had 2 fuels, U-235, U-238, and 1 moderator carbon. Your book, for some reason, just like they did in the first example problem, decided to lump everything together into natural uranium. But we know we don't have natural uranium. We have enriched uranium, so you have to account for all of that. So you have to come up with the individual volume for each of the materials, come up with a total volume, divide that into Avogadro's number. Then when you multiply that times the number of moles, you come up with the individual number densities for each of the materials there. Then based on that, you can go back and calculate sigma transport and sigma A, which we just did. When you do the math for sigma A, the book was incorrect when they had this, because everything is thermal, so that's only considered if it's epithermal. Remember, everything we're doing here is strictly thermal. If you read in other textbooks, if you ever heard something called one group theory, I don't know if you've read that in anything, or maybe Professor Abel mentioned it. When you work one group theory, we consider all neutrons are thermal. If we go to two group theory, one group is always thermal, and then the other group is everything else that you lump into one group, which is a combination of epithermal and fast. A typical reactor today, when they look at what is going on inside that reactor, that they really want to pinpoint what's going on, they have 17 group theory. One group is thermal, and then they break down the remaining 16 groups into epithermal or fast, and they'll pick boundaries depending upon what the fuels might be and particular behaviors that they're looking at. We're going to get a little bit into that later this month or early into December. But right now, everything is thermal, one group theory. So when we have these other, you can calculate this, you can calculate this, and then we go back to L squared, which is defined as 1/3 times the macroscopic cross-section for transport times the macroscopic cross-section for absorption. We have just calculated those values. You throw those into here and you come up with a value for L squared. And we showed before that buckling is equal to K infinity minus 1 divided by L squared. So in this particular case, our K infinity for the first problem that we worked earlier was 1.898 minus 1. The L squared, and we'll just use the value that they have now or something close to it. We'll just say it was 68. So from this, we can take the square root of this and find buckling. And buckling is going to be some value. This, if we use the value they have, and the units are centimeters to the -1. And again, the buckling, the term comes from the type of equation this was developed on, which is used for calculating buckling in columns. So we now have buckling, just like we have K infinity, for this particular fuel and moderator mixture. So again, in your textbook, in example number 1, which is on page 251, I put a paper clip because I know I'm always going to go back and use that page for calculating K infinity. Likewise, I put another binder clip on this page, which is 260, because I know I'm always going to be coming back here for whatever fuel and moderator mixture I have in order to calculate buckling. So, we have just calculated buckling. And this buckling is solely based on fuels and moderators. We have never said anything about the shape that we're going to put this in. So the quiz that I've given you, and let me send that, well, you already have that, so let me go back. So if you break out your quiz assignment, okay, if you look at the quiz, what I've asked you to do is to go back to the quiz we've just finished, which is number 11, which looked at beryllium, uranium-233, and uranium-230. That should be 8 there. And I want you to calculate buckling for that mixture. And then for extra credit, knowing buckling, let me know if you can determine what the effective multiplication factor is, because we've started to account for leakage. This will be due at the start of class on Wednesday. So again, for the quiz we just had where we calculated K infinity, and we had a unique fuel moderator mixture between beryllium U-233 and uranium-238, I want to know what buckling is. Any questions on the quiz? Again, it'll be due at the start of class on Wednesday. I'll see if we have a volunteer to put theirs up. If not, I'll put my solution up. If there's no other questions on this,
So
what I do is, yes.
the word after hour is earlier? Is that what that word
Let me
is?
go back. Let me go back again. Okay. On the quiz, where am I looking at?
The word right after hour, is that earlier?
From our earlier, yes. For our earlier beryllium, uranium, 233, that should be 238 mixture, calculate buckling.
Okay, thank you.
Again, when I make up a quiz, what I usually do, I make them up ahead of time. I put them in my save folder, and then I go back and check them out one last time. I had made up I made up this quiz, and I made up your materials quiz earlier, but Friday was just a zoo all day long. I was here till 8 o'clock handling registrations. I not only have all you guys, I've had to adopt 39 mechanical students because there's just nobody here to do anything. So I had people bopping in all day, and when I put this, I thought I was putting it in my save folder, but I sent it out. So again, I noticed that one little mistake at the very top because it's beryllium, uranium-233, and uranium-238. Any other questions on the quiz? This will be due at the start. And again, nobody's been doing their solutions. I'd encourage you to do that because that gives you extra credit towards your final grade. Okay. Any other questions on that? Okay, before I start into the materials, I want to just discuss what's happening for the next couple of weeks. Okay. This is today, we're having class. Wednesday of this week, we're going to have class. On Monday of next week, I'm involved in a virtual accreditation for ABET for a college in South Carolina. And that's going to involve Sunday, Monday, and Tuesday. So just like I did last month when I was involved with the virtual accreditation of a university in Missouri, I'm going to see you a little bit in the afternoon that day. I'm not sure exactly when right now because they're still arranging the interviews that I have to give to faculty, alumni, industrial advisory committees, the dean, etc. But I know I will have some time that afternoon, sometime between 12:30 and 3:15, where I can meet with you briefly. Then we have our regular class on Wednesday the 10th. Then the following week, we have regular class on the 15th. On that Tuesday, we have URI Trip 1 for part of you. Regular class on the 17th. This again is Trip 1 on that Thursday for the rest of you. Again, we're not doing anything on Friday because the reactor's not available. The following week, which is the week of Thanksgiving, on this Monday, the 22nd, we'll have class as usual, and I will give you take-home exam number 3 for Reactor Theory. This will be due the week after Thanksgiving, and I'm going to give you multiple fuels, multiple moderators that you're going to have to determine K infinity, buckling. You're going to have to put it in a shape that I select. You're going to have to make sure that it goes critical. And then there'll be some other things around that. My guess is if you've been following and you're up to speed on everything, it's going to take you 5 to 7 hours to do that exam just because it's long, but you have well over a week to do it. So you can do it whenever you want to. You can do it Thanksgiving Day after you've been stuffed with turkey, or you can do it over the weekend. You can do it right away. On the Tuesday of that week, I'm going to have the optional lab at URI. And I'll wait to see how many of you want to go. For those of you that go and just attend the lab, I will give you extra credit. If you go to the lab, witness the lab, and then you do a lab write-up, I will give you extra credit. But again, this day, which is the Tuesday of Thanksgiving week, is strictly optional. Then when we come back after Thanksgiving, we'll have class on that Monday. Tuesday of that week, we'll have the second and final trip to URI for the Tuesday people. Regular class on Wednesday the 1st. On Thursday of that week, we'll have the second trip for the Thursday people going to URI. On Friday, what I'm trying to set up now is historically the first Friday of December has always been the in-person meeting date for my 33-member Nuclear Advisory Committee. And there are people from all business and industries, not only in Connecticut, but nationally, as well as department chairs from baccalaureate programs that you might normally go to. Usually I have people involved with business and industry that might be hiring or looking for summer internships to come in before our regular meeting. So if our meeting starts at 11:30, I might have them come in at 10 o'clock. Likewise, the department chairs from the baccalaureate programs that you might normally go to, for nuclear, UMass Lowell, health physics, UMass Lowell, mechanical, UConn, and mechanical, University of New Haven, and there might be others. They're also here in person, and they again come in about an hour to an hour and a half ahead of time. And then I invite you, the students, to come in and meet with them one-on-one over that hour and a half to introduce yourselves. So if you're looking for somebody that you might want to go to work for, you might bring a resume, and you might talk to the people of Electric Boat, Marion, Canberra, Westinghouse, whoever is here, about jobs they might have, and they're getting to know who you are, and you're handing them a resume. They know your interest, they know your name, there's a face to go with the name. Likewise, if you're going off to, let's say, the nuclear program at UMass Lowell, health physics, UMass Lowell, because that's where most people go, those department chairs are here, and they can talk to you about anything and everything. What about housing? What about what you take each semester? What are the costs? How about part-time jobs? Anything and everything. And again, having them here, you know their name, who they are, they know your name and who you are. And you can start a dialogue such that if you want to change what you're taking for the spring semester to better transfer into a baccalaureate program, or on the other side for employment, if an employer says, gee, it'd really be nice if you had a course in this, you can tweak your schedule to make yourself either better employable or better transferable. And you establish the face-to-face contact. We were unable to have a meeting last year due to COVID, and this year, due to COVID protocols, primarily spacing, wearing masks and all this, we've decided to make this a meeting where I'm just going to send to them a listing of everything that's going on in the program at a time, and then entertain any questions to the group going back. But I'm trying to set aside this Friday and pick a time, let's say 12 to 1 for employment, and let's say 1:30 to 2:30 for transfer. And I'll have an invitational WebEx going out to any of the employers and to any of you that want to meet with employers, and let you have a one-on-one virtually. So you have your camera and microphone, they have their camera and microphone. You can exchange all those good information. And then after that, I'll have another period WebEx invitation for those department chairs for baccalaureate programs that are available. And any of you that want to go to a baccalaureate program, again, we'll have a separate invitation to chat with those people about anything and everything there. One of the things I did on Friday is I made up a summary of the program, sent it out to all 33 members of my advisory committee. And I particularly ask those employers if they could come back at this time on that Friday, December 3rd. If not, to pick another common time. Likewise, for the department chairs, I offered a time, but again, I would select another time. And I picked it in the afternoon because I realized you might have your electrical labs in the morning, and I want to make sure anybody that wants to attend is available. Once that is firmed up, I will let you know. And if you're at all thinking of going on to continue your education, I'd encourage you to go chat with this group. If you're looking for a job right away, I'd encourage you to go talk to that group. But I'll give you more particulars when I have that. But this is sort of the schedule of what I plan to do for the rest of this month through the first month of December. I am hoping to have by Wednesday of this week the materials that I need to send you for the first URI trip. And remember, the first trip, whether you go on Tuesday or you go on Thursday, when we get there at 10 in the morning, we're first of all going to have a safety overview for their system, and then we're going to have a really detailed tour. Then we break briefly for lunch, and you can either bring your own brown bag lunch, you can eat inside, you can go outside, and they have tables out there that have an incredible overview look of Narragansett Bay. You know, if the weather's nice, go outside. You can run down the street to get Dunkin' Donuts food or drink or Subway or something and then come back. And then in the afternoon, we're going to do 2 experiments. And then whenever those experiments are over, you have all your data, you feel comfortable, you can leave. We're going to have that exact same thing on Thursday of that week. On the Tuesday, optional for URI, we're going to have 1 lab that we do if you decide to go. And I'll have 1 group that'll, depending on how big the group is, if I have to break you up. If it's a smaller group, we'll just go at 10 in the morning. The experiment's about 2 hours, and then we're done. If there's a goodly number of you and we have to make 2 groups, I'll have 1 group go in at 10, do the same experiment that you'll do at 12:30 in the afternoon. I already know that's going to be on measuring neutron flux. And then the final trip to URI, which in this case will be November 30th, 1 group, or the 2nd of December. We will go there again at 10 in the morning, and that day you'll do 3 experiments. And whenever you're comfortable with everything that day, you can just leave. And the lab write-ups will be due whatever that, I think it's the 3rd Wednesday of December. I'd encourage you to turn them in before then, but I'll leave that up to you. I'll go over more of this later. Any quick questions on the schedule? Okay. If not, let me go and do a little nuclear materials. Before I forget that, in regards to the URIs going on Tuesdays and Thursdays, as I mentioned to you last week, we're unable to go on Fridays due to complications there with their reactor, problems being resolved by NIST in regards to fuel cracking. Not necessarily there, but they're checking out all the reactors, and they have to set up the reactors to do certain experiments. We're not doing them in the order that we normally would do these because of that issue, and we can't go on Fridays. And I asked the 8 of you that were on Fridays to get back to me to move to either a Tuesday or Thursday. So far, 4 of you have done that, 4 of you have not. I need to get that information to URI by the end of the week so they'll know exactly how many they're having on each day and exactly who they are, because they have to do little background checks on everybody beforehand before you go. So the 4 of you that have not told me which day you want to move to from Friday, you need to do this by this Friday. If not, I will randomly assign you to a Tuesday or a Thursday, and that's what it'll be going forward. So if you do have a preference, you better get back to me before Friday for the 4 of you. Okay. If we go back for pure bending, Remember, if we took a bar and we look at individual lengths in this bar, where everything here is L sub 0, and it's not stressed or bent at all, and if we apply a bending moment, and if we go back and we consider this eraser, I put my fingers like this, and I bend it down like this, this is going to make this deform like this. So if we apply this type of moment to create this type of shape, we call this a positive bending moment. So this would be a plus M. And we said it's a plus M if we create a smile. When you've applied this bending moment, if you go back and look at these lines, you'll see that the ones on top have shortened. The ones on the bottom have lengthened. So that the L here on the bottom is greater than my original length. The length on the top is less than the original length. And there will be one line that is exactly the same length as it started. We label this NA, where NA stands for the neutral axis. And the neutral axis, when you look at it in this view, it appears as a line. When you look at it in this view, in other words, when you rotate it 90 degrees towards you, this will also appear as a line. So it shows up as a line this way, it shows up in a line this way. So the neutral axis is really a neutral plane. So if this is being shortened, we can say that this system is in compression. If this side is lengthened, we can say this is in tension. And what I do, or what I recommend, is whenever you go to work a problem and you see the moment that it's been created, I immediately write on the top surface, bottom surface, top surface, bottom surface, what we are experiencing. So in this case, we know the top is in compression. We know the bottom is in tension. Likewise, in this view, we know the top is in compression and the bottom is in tension. We don't know anything else right now, but we know that that's true. And if this is the neutral axis where the length has not changed, then it's neither in compression or tension. So this is unstressed. Whenever we talk about tension or compression, we end up talking about plane stress. So in just looking at this, if it is unstressed on this neutral axis, which means sigma is exactly equal to 0, as we go away from the neutral axis towards the top, we'd expect sigma for compression to increase. Likewise, the further we go away from the neutral axis to the bottom, we expect sigma tension to increase. And in particular, on the top here, we expect to find the maximum value for compression. In this view, it would show up here, so this is sigma compression max. Over here, we go all the way down, this would be sigma tension max. So over here, this should show up as tension, sigma tension max. And again, along the neutral axis, this is exactly 0. So the further you would go away from the neutral axis, the more the stress increases. The maximum values are going to occur at the outer points. So therefore, if failure, so sigma ends up being greater than my yield value, when it fails, it's going to fail on either the bottom, if it's in tension, or the top, if it's in compression and it reaches that maximum value which exceeds the yield value. So now that we know this, how are we going to utilize that? And the first thing we need to do is define or find out where is that neutral axis or that neutral plane. So is the centroid of cross section area. So for example, if we are bending something like this with a positive moment, we turn this sideways like this, and my cross-sectional area is 2 centimeters by 6 centimeters. Okay. The centroid of this section is halfway up this, so half of 6 is 3. This would be my neutral axis because it is the centroid of the area. So this is 3 centimeters from the bottom, 3 centimeters from the top. So in this particular case, the bottom is in tension, top is in compression. So sigma max for tension would be exactly along the bottom. Sigma max for compression would be along the top. And since this surface is equidistant from the neutral axis as this, in this unique case, sigma max compression is exactly equal to sigma max tension. This is a very simplistic case. How do we find the centroid in other shapes? So, let me give you a T-bar. And in this case, let's say my bar looks like this, where this is the length. And this dimension is 2 centimeters, this is 6 centimeters, this is 2 centimeters, and this is 10 centimeters. Let's say this is symmetric. I haven't drawn it particularly symmetric. But this is my length, and let's say this time I put a negative moment on it. So when we do that and we look at it, we can hopefully see that the top is elongating, so this is in tension, the bottom is in compression. We don't know where the neutral axis is. If we come over here, we know the top is going to be in tension, the bottom is going to be in compression by that same logic. But we need to find the neutral axis. Neutral axis is defined as the sum of areas times their centroids divided by the sum of areas. So this will be from 1 to n, depending upon how many shapes that you have. When we go to do this calculation, we establish a baseline to standardize our results. You don't have to, but most select the bottom as the base. So in this particular case, looking at this, this is my baseline. So my equation for calculating the neutral axis says we have to sum up all the areas times their centroids, then divide by the total sum of areas. And then what that does is it finds the centroid of this cross-section shape. Okay? So when we look at our shape that we have, when we look at this, hopefully you'll say to yourself, I see two different shapes. I see a rectangle there, and I see another rectangle there. So if I do that, down here I'm going to have the area of one times its centroid plus the area of the second one times its centroid divided by the sum of areas, which is A1 plus A2. If you didn't see it that way, let's say you said, I see this as really being one rectangle there, another rectangle there, and another rectangle there. So if I use the same equation, this time I'll have three components. So no matter which way I do it, you're going to come up with exactly the same result for the neutral axis calculation. So when you go to work these, there's nothing wrong with having 1, 2, 3. The more shapes you have, the more chances you have of making a mental or mathematical error. So I would go with a minimum number of shapes and then do my work. So in this particular case, so if I look, I'm going to just move this over here. So if I look at this area, area 1, it is 2 by 6. Okay. And its centroid is exactly in the middle of this, and that's part of the reason we have a baseline. Because if the centroid is right there, it's going to be half of 6, which is 3 centimeters. So the y distance from my baseline is 3 centimeters. If I look at the second one, this one is 10 centimeters by 2 centimeters. Its centroid we know is here. It's half of 2, which is 1. But to get them there from the baseline, we have to go 6 plus half of that one. 2 is 1. So this is 7. Again, I'm going to divide that by the total areas, which is 2 times 6 plus 10 times 2. So let's see what that would be. We're going to have to sort of work this out. Okay. So this is 12 times 3, so this is 36. This is 7 times 20, so that's 140. This is 12 and 20. So this is 176 divided by 32. That's going to be about 5.8, something like that. Somebody have a calculator? $5.5. So that tells me that the neutral axis, which is unique to this particular shape, is at 5.5 centimeters from my baseline. So if this is 6, this is my neutral axis. If I do it in this view, this distance is 5.5 centimeters because this is my baseline when I rotate this thing 90 degrees. Okay, so if that is a neutral axis, and we've already said that the bottom is in compression and the top is in tension, anything below the neutral axis is in compression. Anything above the neutral axis, including this little part, is in tension. And in looking at this, I would always label this distance from the baseline, so this is 5.5 centimeters. And then in just looking at this, if this total thing is 6 plus 2, 8 tall, then this side has to be 2.5 centimeters. So in looking at that, since we know plane stress appears to be linearly related to the distance from the neutral axis, in this particular case, since this is the furthest point away, 5.5 from the neutral axis, this is where the maximum value for compression occurs. It is also where it will fail if sigma exceeds sigma yield. When we meet on Wednesday, we're going to develop the equation where you can find the plane stress at any point in a system. And this is going to be the moment applied, y divided by I, where this is the applied moment. This is the distance from the neutral axis to the point of interest. I is the rectangular moment of inertia. This is a physical property of the cross-section, and it's basically taking the area and it's swinging it around the neutral axis to come up with a moment of inertia. This moment of inertia is similar to what you did for torque, where we had J, which was polar moment of inertia. So if you look at the 3 pages I gave you at the start of the semester, the first page has yield stresses, ultimate stresses, E values, G values. If you open that up, you'll see that it also includes there are 2 pages. So the first page is such things as yield values, ultimate values, yield values, ultimate values, E values, G values, densities, all that good stuff. The next 2 pages one looks at shapes and identifies the centroid of that shape. It'll also tell you the area of that shape, because you'll need these in calculating the neutral axis. And then the other page talks about I's, or rectangular moments of inertia for any shape. So you'll see it back there for rectangles, for circles, for semicircles, for ellipses, for semi-ellipses, for triangles. Anything you want, it'll have the rectangular moment of inertia. On the previous page, it'll have how you calculate the area of that shape, as whereas where is the centroid of that shape that you need to calculate the neutral axis. So the quiz I'm going to give you now is going to be due at the start of class on Wednesday. We'll go over this in class. And let me send that to you very quickly, and then I'll discuss that with you. Okay, I've just sent that to you, so let me have you open that up. And if you have that, this quiz is worth 10 points and it's due on Wednesday at the start of class. So I've given you a beam, and I'll sketch this beam up on the board in just a minute. And on the bottom, it has a semicircle. It has a radius of 5 centimeters, connected to a rectangle, which is 2 by 6. And on top is a triangle, which is 8 centimeters by 4 centimeters. I'm telling you it's symmetrical, and I'm telling you it's one rectangle, one triangle, and one semicircle. I want you to calculate for that shape the neutral axis. And then for extra credit, and this is true or false, the location of the neutral axis is independent of the material. True or false, and I want you to justify your answer. That's worth 2 points. Again, this is due at the start of class on Wednesday. Any questions on that? Because I'm now going to sketch this up on the board.
Are we to assume that the base is under the semicircle?
Yeah, well, you can establish the base wherever you want it. I would encourage you to always put the base at the very lowest point of whatever the cross-section looks like. Okay, if I go back to my camera, okay, which hopefully you can see, I've resketched this here. Again, you could draw the baseline wherever you wanted. I would encourage you. I would encourage you to always use the bottommost point. Okay. So I'm showing it to you in this view. Notice I haven't told you yet whether I'm applying a positive moment or negative moment. It doesn't make any difference when you're calculating neutral axis. If I turn this thing sideways, it would have some length. And if you looked at this thing, when I rotate it 9 degrees, if you looked at it sideways, this is what you would see. This line represents the differentiation between my semicircle and my rectangle. This line represents the differentiation between my rectangle and my triangle. So when you have finished this, you're going to calculate for me a neutral axis, and I want to know what that value is from wherever you established your baseline. That is the quiz for Wednesday. And then on Wednesday, I'm going to give you another quiz due the following Monday. And then what I'm going to do is apply a moment to this, and then ask you to find some stresses. I might make it a material to ask you if it's going to fail, where it's going to fail, that type of thing. Any questions on this quiz?
Okay.
It's not that hard. I'm guessing it would take you 10 minutes maybe.
Okay. It being symmetrical, the base of the triangle at 8 centimeters is the same as the base of the semicircle. Is that correct?
This entire thing, although I didn't draw it very well, is symmetrical. So in other words, this isn't offset, something like that. This is symmetrical.
So I understand that. So you have an 8 centimeter dimension at the top, and I'm just saying that that is both the base of the triangle and the base of the semicircle are 8 centimeters across. That's how I'm interpreting.
Semicircle radius is 5 centimeters. So you should be able to figure out what that dimension is. You understand that, Ty?
Yes, I understand. Thank you.
Any other questions from anybody on this? So again, we have the 2 quizzes that will be due on Wednesday. I'm going to go over those 2 quizzes, and then I'm going to continue to lecture. In the material side, I'm next going to use the same shape for a take-home quiz from you, but I'm going to give you another example. We're going to apply a moment. We're going to give you a particular material that this is, and we're going to look to find out various stresses located throughout it. On the reactor theory, we're going to take, once we now know buckling and we know K infinity for our fuel moderator mixture, we're going to take the example in the book, which used the 235 in graphite, and we're going to apply that to an infinite slab to find out what's going on. And then I'm going to apply it to a cube. We're going to find out what's going on. And then for your take-home quiz after that one, I'm going to ask you to do certain things with the material you have, which is the beryllium and the uranium-233. So for these next couple of quizzes, we're building off the last quiz. So I always want to work them uniform so you'll have the exact values you need for working the next quiz. I will be around today to my usual, probably 8 o'clock or so, just getting administrative stuff done. There's probably 2/3 of you that have registered so far. So I'd like the rest of you to register this week. I probably have a quarter of the release forms. Those are very easy to do. I'd like those back. And then sometime over the next 2 weeks, I want you to complete the graduation application form online. And I'll get a copy of that. So far, the only one I've got back is from Sarah. And then I want you to submit to me your plan of study signed and dated. I'll review it, and then I'll turn all of those in 2 weeks from today to the registrar once I know I've had that you all applied for graduation. If you have to do any course substitutions, I would like for you to do those within the next 2 weeks. At the same time I turn in all the plans of study, I want to give to the dean any and all course substitution forms so we can look at those in mass rather than separately, and hopefully you'll just approve them lickety-split, and then you're good to go. I noticed that some of you did not register yet. And the dean is going to start to make decisions definitely before Thanksgiving when he looks at registration numbers as to whether they have to cancel certain courses or labs. Obviously, that might impact you if you need to have 1 or more electives, or you're looking to take other courses or labs that you might want to transfer to a baccalaureate program or to make you more attractive to get employed. So I need those. The other thing is, if I have not heard from you from registration by the end of this week, particularly I have to balance out the labs for the simulator. I can't have more than 4 people per lab. So the people that have taken the time to get their registrations in on Friday or get them in the first part of this week, I'm sort of giving them first dibs on the lab spots. So I want everybody to finish your lab selections when you turn in your registration forms so that I can balance labs. If I have not heard from you by the end of the week, then I would just put you in any open slot going forward where there's a slot in a simulator lab. So it could be on a Monday afternoon, Wednesday afternoon, anytime on Thursday. It's whatever's available. I'm not going to penalize the people that have taken the time and effort to get me their registration materials early on. So I would like to get everybody back, or otherwise you'll just be subject to wherever I put you. Any questions on anything? Again, I'll be here till 8. I might be here tomorrow. If I do, it'll be after 6 o'clock for a couple of hours. And I'll be here all day on Wednesday. And I'll be here Friday afternoon for sure. Is So nothing else, I'll let you go to Professor Lance's class. Again, I will be around today till 8 o'clock if you need to see me on anything. Otherwise, see you Wednesday.
Professor Sherrard, I have a question.
Sure.
I was a little unsure where you were saying that the maximum tension and maximum compression was, where it was.
Okay, I didn't, in this particular case, I haven't even mentioned.
Well,
Let's
referring to the last problem that you were going over, the one with the T, I know that the neutral axis was 5.5 centimeters, I think.
Right. All right. Let me do it on this one, okay? Since it's already up on the board. Let's say I gave you a moment of 20,000 Newton meters. Okay? Positive moment. Whenever you find where the neutral axis is, let's say when you finish calculating, let's say it is right there. Okay? We know because this thing is in a positive moment, we know the top is in compression and the bottom is in tension. And we know exactly on the neutral axis, the plane stress is exactly 0 because that length of that line has not changed in dimension. The further away we go from the neutral axis in this way, my compressive plane stress gets greater the further away I go. So that on this very top is the maximum value for compression. Conversely, when I go the other way, the tensile value of plane stress increases so that on this bottom I have the maximum value for tension. We're always worried about failure. So for bending, we only have plane stress. So we're always looking where the stress we have here can be greater than the yield stress for whatever that material is. So if I told you this was made out of aluminum 1100, we know that this yield value is 95 megapascals. So if ever we have a point where it exceeds this, it will fail. Typically, you look at the maximum value for compression or the maximum value of tension. So if it's going to fail first, it normally fails either here or here. And on Wednesday, we're going to find out how you determine exactly what the stress value is, how you can determine where it's going to fail. Does that answer your question? I hope.
I guess.
Well, re-ask it if you still got a question.
So my question was referring to when we had the T, the T
Okay,
problem.
let's go back to,
We had the neutral axis at 5.5 centimeters after calculating it. I was just trying to figure out, was T max 2.5 centimeters, like the maximum tension? Because that's
okay, so this is 2 and 6, 2 and, what was the other dimension?
the top value was 10 centimeters.
Okay. So we calculated the neutral axis. And the neutral axis was 5.5 centimeters from the baseline. This top surface then is 2.5 centimeters because 6 plus 2 is 8. 5.5 plus 2.5 is 8. Okay. I haven't told you anything yet about the type of moment applied, what the value is, or whether it's a positive or negative moment. So right now, you cannot determine what's in tension, what's in compression. But the one thing you do know is, if this is a neutral axis where by definition, plane stress is exactly 0, since the bottom is the furthest away from the neutral axis, this is going to be the maximum value for plane stress, no matter whether it's compression or tension, and you can only determine that when I tell you what type of moment is applied.
All right, thank you. That makes more sense.
If this thing is going to fail, not knowing anything else,